Alright guys, today we are going to be covering some other functionality of R. Specifically, we're going to be looking into the creation of functions, a little bit of data manipulation, and hopefully the introduction of a t-test, which is one of the other parts that we suggested to include in our syllabus. Alright, if you remember functions, we covered this earlier in our introduction to Visual Basic, are these very complicated processes that you have to repeat over and over and over again. So you don't want to be, every time that you want to make a calculation, redo the whole process. Visual Basic allows you to include the entire process into a single function, so that all what you have to do is to type the function, enter the data that you want to run through that process, and the function will give you the result. So the same thing that you did in a Visual Basic, we are going to do it now in R. So I'm assuming that you are already located in R. Let's just do quickly here demonstration. So let's just create, for instance, a variable that is called A, and that variable has a number of 1. And let's create another variable that is called B, and that variable has a number of 3. And let's enter just another one that is C, and that is equal to 3. Right? So let's imagine that I want to sum A plus B plus C, right? That value is 6, right? So obviously you can do more complicated stuff. You can do exactly the same summation. By the way, for you to go to take the same code that you just wrote, you can just push the key arrows, the up and down arrows, and that will move you up or down into the lines that you just grow. So we just want to go back to this line. We want to take all of that summation and we're going to divide it by 100, right? Then we want to take the same value, but we want to calculate the log scale of that. So log of that value, right? Let's imagine that now we want to calculate the exponential of that, right? So you type there, right? And you just get the picture of different mathematical calculations that you can enter there. Obviously, the calculations can be more complicated than that. So the idea of a function is that you just enter this one value, these 3 values, 1, 2, and 3, and the function will do all of these calculations and will just give you this one value here. So just let's find out how can you get a function in R, right? So my suggestion is go to the internet, open a new window there, and just click there, how to make a function in R. Again, keep in mind that one of the things that I would like to do on this class is not so much for you to learn what I'm teaching you, but also for you to learn how to do things on your own, right? So which is the reason why I want you to learn how to find out the necessary information for you to do this on your own. All right, so let's do this quick search here, how to make a function in R. So you get a lot of different web pages there. And here's, for instance, one pretty neat, how to create a function in R. Let's just see what it does. You can just screen over that. Here we found this web page. This is the first time, by the way, that I see here. So usually I don't really take a lot of time reading this, but obviously you just need to spend more time on this. Today I'm usually getting pretty good at reading over the code, but now that I scroll down, I can see, for instance, this thing here, and it just gives you a name, which is the name of the variable, something that is called a function. The function, the things between brackets, are the variables that you are going to enter, right? Now, the process that you are going to run in that function is separated by these curly brackets. So what this function does, it calculates first a variable that is called the percent, round, just rounding up the number, x, which is the value that you enter, multiply that by 100, you round that to 1 digit. And you get the results, which is pretty much paste, which is just joining the percent, which is the variable that you created, plus this percentage sign. The separation is simply a quotation there. All right, let's just run this equation quickly. Let's just generate that function in R. So the function, we're going to call it calculate percent, right? It's going to be equal. By the way, in R, equal is usually described with these two signs there, but you can also type equal. So right now, the adopted standard in R for you to name variables and put equals is with this sign here, right? So calculate percent is going to be a function, right? So we're going to name a function there. It's going to require one variable. We're going to call that variable X. We can call it A or B or whatever name you want to put on it, right? So in the tutorial on the internet is X. We close it. Then we open the curly brackets. Keep in mind the curly brackets are the code that is going to be run by that function. So let's go back there. So the first thing is percent, right? And percent is going to be equal to round X. We multiply by 100, and we are going to round that to a digit, to one digit. Close that between brackets, and we can close brackets. Sorry, I made a mistake here. All right, so I don't think this is liking it for me to type the function directly. So we are just gonna, for now, open a Word document so we can paste the function there. Just copy the text that I just wrote there so I don't have to do this again. So basically, the problem that I'm having here is the fact that in in R, every line has to be run simultaneously. So in this case, the function has multiple lines, so R doesn't really like that. So what it means is that you need to develop the code outside R so that you can potentially get different lines simultaneously in R. R is very unlikely that it's going to let you have multiple lines of code being part of the same function there. All right, let's just go back here. So I have my function here. The first thing that I do, again, in that function is to calculate a function that is called percent. That percent is going to be equal to round X, which is the value that I enter. Multiply by 100, I digit to 1, and then I'm going to enter another variable that is called result, and that's going to be equal to paste, which again is just merging the different strings, a test with a number with a number. I'm going to paste percent, and to the number, which is the number that I calculated here, this variable percent, I'm gonna attach the percent sign. So, and the separation is just an empty space, right? Then this function, I want it to return to me the result value, right? So you can just copy this, paste it now in R. So there seems to be an error here. Oh, it's the way in which I type function there. So it's function. Okay, very good that I found that mistake. One of the first things, whenever you encounter those problems, R is pretty good at telling you where the errors are, right? So when you saw I copy and pasted this function here, the error is in the first line. So obviously there is something wrong in this first line. So you look at it, obviously the problem here is that I misspell the word function. So Excel obviously doesn't recognize that. So I just corrected that here on the test file. So I copy that again. and now I run that function in R. So R now has a function that is called percent, right? So on the function percent just takes a number that you enter, it rounds that number, so it multiplies that number by 100 and it rounds it to 1 digit, and once that's calculated, then you add the percent sign to that number, and that's the result that you get after you type that function percent. All right, so let's just confirm this. So I'm gonna type the calculate percent. I'm gonna open my brackets and I'm gonna put so the variable that is required is x, so I'm just gonna make x2, click enter, and then I get 200%, right? Again, if you look at what the calculate percent is doing, is basically taking that number that you enter here, multiply by 100, round it to 1 digit, and then it adds the percent signs. So again, if you enter 2, multiply by 100, round it to 1, you get 200, add this percent sign, and that's what the percentage calculate percent function return to you. And obviously you can create your own functions, and of course they're gonna get a lot more complicated. We're talking about 1, 2, 3 pages of code that you can run on a single line of code. Again, the importance of these functions down the road is the fact that very quickly you will see that code gets very big, right? So, and you want to be able to find out where the errors are. So it's good to always try to cluster your data into functions so that if there is an error in your code, you don't have to go through 40 pages of code. You just need to find out what the function, where is the function that is giving you the problem, and that of course allows you to spot easier where the potential errors could be. All right, so that's how a function is done. So before we move on forward, I wanna show to you a program that is called ThinR. I recommend you to download that. Just go to the internet again and type ThinR. There you have it. And you can download it from a couple different web pages. I mean, I installed mine many years ago, but here you can, for instance, see it. You can download it from there, but there are several other pages where you can download this stuff from. And basically, this program here. And this is the program that I commonly use to keep my code. Again, a lot of people probably have recommended to you to use RStudio. RStudio is a great development. You obviously had become very good. They had improved quite a lot. Unfortunately, I already lost that boat, and I prefer to use to run my code directly directly in R. And I like to keep my codes always organized on this program. All right, so let's go back to our function. Again, we had, you scroll back up. We wanted to do a function that does all of this kind of stuff. The exponent of log of a plus b and c, right? So again, if we want to replicate that as a function, we can call it do weird things. That's gonna be the name of our function. That's gonna be equal to function again. We're gonna enter 3 variables, a, b, and c, right? So what do we want to do? So just open the curly brackets. So we want first calculate the sum, where you're gonna generate a variable that is called the sum, and that's gonna be a plus b plus c, right? Now what do we want to do next? We want to do a division, right? So we call it a variable division. That's going to be equal to sum, to the variable sum that we created above, and we're going to divide that by b, right? Now let's do something else here. Let's calculate the logarithmic of that. So we are going to call it log, and that's going to be equal to the log of the thing that we just calculated, which is going to be called division. Let's just code it there. We're going to return then log, and we close our function. Right, let's summarize quickly this function that we just created there. Again, this could be a lot longer, probably obviously a more complicated process. So we had here a function that is called do weird things. That is going to be an Excel function. You can see R, this program, thin R, allows you to see variables that are already, functions that are already in R. So for instance, when you get this red or blue coloring, that means that those are already functions from R. Okay, so what do we have here? Again, we have a function that is called do weird things. It's a function. It's going to require three variables, A, B, and C. The first thing that it does is to calculate a variable called sum, which is equal to the summation of A plus B plus C. Then there is another function, another variable, that is called diff, and that is equal to the sum variable that we created just above this one here, and we're going to divide it by B. Then we're going to calculate another variable that is called log, that is equal to the log of the variable that we just calculated. And once all of that is done, I want my function to return to me the log variable that we just calculated. So let's run this. I hope that you can see already that there is an error on that function. So okay, so we run this. So we noted an error here on this line. So take a moment to think what could be the error there, right? R sometimes actually gives you some hints into where the error is. So here it tells you there is an error and there is an unexpected bracket, right? So you look at our function, obviously the error that we had there is that we didn't close that bracket there, right? So we had the opening bracket, but the closing bracket, but we don't have an opening bracket there. So let's fix that error. Let's go back to our thin R. We close the bracket. Now we copy the function, and we're going to run the function again in R. So the function is done, right? So now R has a function that is called do weird things. Now let's run that function. So we type do weird things. As I told you, as you saw, it requires three variables, A, B, and C. So A is going to be equal to 1, B equal to 2, and C is equal to 3. Then I click enter. Now, it's an error here, right? It says error in your function. And basically what it tells you is it couldn't find the function return, right? So I did that on purpose. So just for you to see how to debug some of these problems. So really, obviously my problem there is that I misspell that the return in the result, right? So I go back to thin R, and now I correct that spelling mistake there. Now, as soon as I corrected that spelling mistake, you see how now that word turns red. That pretty much tells you that there's a function that is already in R. So I copy that function, and now I paste that in R. Now again, let's test our function that is called do weird things, and it has three variables, 1, 2, and 3. I click enter, and then I get my value there. So again, it's the way in which functions are run in developed in R. Obviously, you can do a lot more complicated stuff in there. Now, what I want to do a tutorial today with some practical applications, and we're going to be trying to do some, again, creation of some functions, some data manipulation, and hopefully some statistics. Let's see how far we can go today. So for that, I'm going to give you two databases. I will email them to you later. They're on my hard drive here on the F drive. They are here under presentations, methods, class 3. So I'm gonna send to you these two files, right? And basically what they are is just the heat waves that are there in the world today in 1950, and the ones that will be there in the year 2099 from the IPCC report. So these are just a couple of files that that we are working on in another project. So I figured that we could potentially just use these two files today as an example. Let's just open one of them for us to see the structure of this database. So as you can see, my phone is already start getting big there. So when you open that file, this is what you get. Again, we had the cell ID. That is, right now we have the entire planet divided in cells of 1 by 1 degree. So this is the cell ID. This is the number, the heat anomaly. This is the humidity. This is the percent excess humidity. This is how far from the normality, from the average humidity that heat wave was. Again, if we select that row there. So this is a heat anomaly that happened on this cell. This is the cell, that's the first heat anomaly of the year 1950. This is the humidity during that heat anomaly. We had, this is temperature, these are the winds, this is called solar radiation, days to the summer. This is here the start of the heat wave. So that heat wave, it starts in January 11 of 1950 and it stopped in January 11 of 1950. So this heat anomaly was only 1 day long. You can see here in the duration. Now if we look at this other heat anomaly here, this heat anomaly started on November 19. Sorry, hello? Yes, I am in a presentation right now. Can we talk in an hour? What is this about? Oh my God, what happened? Okay, we are on our way. Okay, bye-bye. Okay guys, sorry, I got an emergency with my daughter. I need to find out what this is about. I will continue the second tutorial in a little bit. All right, let's continue here. So as I was telling you, this is a database on the heat anomalies for the entire planet according to one of their system models for the year 1950. And just as an example here, in this row we had, this is the cell ID, this is an identifier for that cell, for a grid. This is the heat anomaly number 12, this is the percentage humidity on that place. And over here you had the start date, the end date, and it lasted for about 8 days. All right, so what I want to do with these couple files today is to see if first there are differences in the number of heat anomalies between 1950 and the year 2100. So are the two files there. You remember here on the files that I just submitted to you. And where are we now? Courses, stations, methods, class 3. So here, those are the two files that I'm going to submit to you. So we had the heat anomalies for 1950 and 2099 according to one emission scenario, and we want to find out if the number of heat anomalies was different on those two places. All right, so here we're going to go to our TIN-R, right, which is the program where we're going to develop the code, and we're going to start from here. So we're going to start by creating a variable that we're going to call heat 1950. By the way, R doesn't allow you, doesn't accept naming variables with numbers. So every time that you name a variable, it has to be start with a letter. So for instance, I cannot create a variable that is called 1950 is equal to 5, let's say, right? So in this case, we will say this is a variable that is called 1950 and I want the variable to be 5. R doesn't accept that, right? So you actually need to, you want to generate a variable, you have to enter a letter at the end, at the start of that. And now you do have a variable that is called x1950 there, right? All right. So let's go back to our TIN-R. So we're going to start a variable So the first thing that you need to do, and that's one recommendation that I want to give you, is to always that you write a code, explain what the code is, right? Right now you are probably very familiar with what you are going to be doing, but in 2-3 years you might want to go back to this and you need to understand what this is about. So anytime that you are doing something new, you should probably describe it there. So we're going to say this is a code to compare heat anomalies between 1950 and 2099. You can add this was done by Camilo in October, November 4, right? So just try to keep a catalog there of what you are doing. Every time later on that you do a change on the database, or to this code, it's always good to describe what you did here. Again, you just need to be sure that years from now you can come back to this and pick it up quickly. All right, so we're going to introduce a variable. We're going to call it x 1950, and that's going to be the file that is in 1950. So that's the folder here, right? So you remember from our last tutorial, the way in which you read a file is using the fret function. And again, I will show you something in a second. You just need to enter the name of the path where it is. Right click on the name of the file, click rename, then copy all of that, copy that, Control C, and then paste it here on the name, and then close quotations and close brackets. Right, so just remember that you need to change these things there. So if I run this in R right now, it's gonna give me an error, right? It couldn't find function fret. So I'm gonna give you a second to think what could be the reason for that error there. So the reason for that error, if you remember from the last tutorial, fret is a function that was created as part of a library that is already created. So the first thing that you need to do is to load that library, right? So in our code, we're gonna type library. That's the function to load any library, and the library that we want to load, if you remember, is called data.table, right? So if we copy that, and now we load that file, that library in R, by just clicking enter. Takes a little bit. You say it was loaded. So now we can run our line of code now, and the file has been loaded already, right? That's because again the function fret now is available to R. So that's 1950. We are gonna enter now. We are gonna load now the database for the year 2099. No. And we need to change the name of the file here, which is 1929, and we can just load that file, right? All right, so it says that file doesn't exist, so let's just go and find out what happens. So what happens is that the name of the file is different, so we just need to right click, rename, copy the name of the file, go back to .r, and again replace the name of the file on your string there. And now we can copy this, paste it in R, and just wait a second for it to load. So now we had the two files there, right? So we had the database for 1950 right there, and the database for the year 1999. All right, so just gonna introduce very quickly here something that I don't know if I introduced before. We're gonna do a plot. Let's for instance look at what is the correlation between temperature and humidity on 1950. right? So we can just copy the name of the database. The way to do a plot, just to visualize the data, is plot, open brackets. You type the name of the database, you use the $sign, you copy the name of the variable. So we're gonna plot relative humidity, which is that variable. You use this sign, you copy the name of the variable again with a $sign, and we are gonna plot that against temperature, which is this variable here, TAS, right? So right now what we are doing here is just generating a plot from the database called X1950 relative humidity, the variable relative humidity, against the database 1950 and the variable temperature. You click enter. There is the correlation for all of the pixels, all of the heat anomalies in the year 1950, right? All right. So that's how you do a plot in R. Obviously, if you want to get more information on how to modify the axis and another stuff, actually, let's just do this plot here between, this is how far from the peak of the summer it was, right? So this is where it happens right at the peak of the summer. This is the number of days. This variable here is the number of days from the peak of the summer when the heat anomaly happened. So this heat anomaly here, they happened 139 days before or after the peak of the summer. I want to compare that against the duration just to see if long anomaly. Let's see just what happens there. I haven't really done that. Oopsie. So I need to copy duration there. Click enter. All right. So this is how far, again, from the peak of the summer a heat anomaly is, and this is how long the heat anomaly was, right? So obviously you get like a triangular shape there. Well, I don't know how to interpret this yet, but anyway, that's how you do your plots. You can, for instance, note the different names of the axes here. So you want to find out more information that you want to change, how to edit this figure. One thing that you can do is type a question mark. So every time that you want to get new help about a function, you type question mark, and then the function, which is called plot, you click enter, and that will bring to you all of the information about that, how to use that function plot, which is part of graphics, which is part of the origin, the thing there in the insights of this. So for instance, here you have main is an overall title over the plot. So if we copy this main, we go back to our plot, we do it again, and here we put comma main, and we're gonna put a name to it, right? Keep in mind, because it's a test, so you need to put quotations. So we're gonna call it heat anomalies 1950 anomalies, close quotations, and click enter. So you can see that main, the function, from this function plot, this capacity of main is what allows you to put a title to your plots. You go back again to the help, you get sub, which is again, is just putting a subtitle there. Xlab is where you want to put a name to the x-axis. So let's see what xlab does. So again, you go back to your R, we're going to type xlab is equal, and we are going to call it to duration, right, which is the name of the x-axis. So you can see how that function there changed duration there. You can do the same thing for the y-axis, and we're going to call it now, as you can imagine, it's probably going to be called ylab equal, we are going to call it peak of summer time, to peak of summer, close quotations. And as you can see, that will put the name to that axis there. So again, if you go back to your help, to the help from that function, you get all kind of other additional information there that allows you to play around with your how to make that plot better. Now, one thing that is very nice about R is the fact that all of the help menus, all of the help functionality of pretty much every function is one of their standards. At the bottom of it, it always provide you with an example of how to use that function, right? So here it gives you just an example. So you copy these 3 lines of code, you can go to your to your R, paste in there. It will give you an example there of how to plot your how to use that function plot. Again, let's just look at another example, like for instance mean, which is the average. Again, it tells you what you need to enter to calculate the mean value, and here is just an example there, right? So this is an example to calculate the mean. So you copy these 2. The mean that gives you this value is 8.75. So what is that example? So what they had done there on the help for menu is to generate a variable that is called x, and that variable x is a database, basically a compilation of numbers between 0 and 10 and the number 50. Let's see what this does, right? So it creates an array of numbers between 0 to 10, 0, so you can see here 0, 1, 2, all the way to 10, and then it adds 50, right? And okay, so that's what this line of code does here, and here then xmem calculates the mean of this variable that you just entered there. All right, anyway, so that's just a trick there. Anytime that you encounter a problem with a function that you don't know how to do it, all what you need to do is again type the question mark and the name of the variable, and Excel R will show you all of the information that is available about that function there. All right, let's go back to our tutorial today. Really what we want to do is to find out if there are differences in the number of heat anomalies between 1950 and the year 1999. So we have those 2 databases there. And what do we want to do? All right, so we are gonna select just, I guess we can select the cell ID, right? Which is the place in the planet where that is, and the number of extreme heat anomalies, right? So what we are gonna do is we are just gonna select some columns. So we don't really use all of these other variables, but we are just interested in counting how many heat anomalies were on every cell on the planet between those 2 places. So let's go back to R. So here what we are interested in is we just want to take 2 columns there. The column of the cell ID, the grid ID, and the number of events, heat anomalies on that place. So we're going to type here how to select 2 columns from data.table in R. You see what kind of tutorials do you get there, right? Again, keep in mind from all of these database that has all of these variables, I just want to select these 2 columns here, right? So here, if I go to Google, I type what I want. There, let's just check out quickly this first tutorial, which I already opened up. So it just describes, again, I want to select 2 columns. How do I do that? And here is an example, right? So basically what you do, you need to load, this is an example here, you load the library, and then you create the table that has 3 variables, columns A, B, and C, and then here you select just columns 2 and 3. And with false is obviously probably some kind of information that it needs to, that Excel, that function will require. All right, so let's just go here. We had, obviously this is the name of the database here, so we select 1950. we want to select columns. If you go back to your thing there, so we want to select columns 1, we want to select columns 2 and 3. So that's fine with false. So let's see what that does. So there you can see it, right? So this function that we just found on the internet allows you to select from a database. These curly brackets then tells you, okay, from inside this database here, what do you need? So what I want, this comma separates the rows. So if I want to just, for instance, the first row, those 2 columns, I can type here 2, and that will give you the second row of columns 2 to 3, right? There you can see it there, right? So because you didn't enter that number, it was empty, it's gonna select all of the rows. Now the next thing after that is to select the columns. So we are selecting columns 2 and 3, and with this function with equals false, it pretty much, I don't know what that does, but I presume that's something that is required for you to actually be able to use this function. All right. So if we go back to our thing R, we're gonna enter here heat. We're gonna generate a new variable that's called heat 1950, heat waves 1950, and that's gonna be equals to the database of 1950 of all of the heat waves of 1950, and we just want the columns 2 and 3. We do the same thing for now 1999, and here we have to select the database 1999 and select again columns 2 and 3. So let's just copy these 2 lines of code, paste them here. Pretty much what happens next is that we have 2 databases, one for 1950 and one for 1999. Now, one thing that we want to do now is to count. We're interested now in counting how many heat anomalies did happen on every cell, right? So right now, you remember from the Excel sheet, you had the cell ID. So these are all of the heat anomalies that happen on that cell number 1. So in this cell, by the way, the geographical coordinates of that cell is this number here. In that cell, there were 16 heat anomalies that happened in 1950, right? So that's what we want to do. We want to generate something that is called a pivot table, in which we just select the one the one number here, and count how many heat anomalies did happen on this cell 1. So we go again, Google is our friend here. Let's find out how we do this. So what we want to do is how to do a pivot table. Data.table in R. Again, the question that I ask is how to do a pivot table in data table in R. So here is a couple examples. Let's see what this one does. So again, it just tells you the important value of the data tables there. So how to do it in R, we scroll down, and okay, this one is probably not being very helpful here. Okay, I don't think this is group by. Okay, what is this one about? All right, I don't think this is very helpful. See this example here. So again, this creates a data table, enter some numbers there. Okay, this one thing here, so you can see creates a database. It has the summatory of these 3 columns, so that could actually work there. Okay, let's see what this one does. So again, we are generating a variable that is called ANS. Use the function that is called decas. Taking this database. So our database is this one here, 1950. You'll see. So you just replace that by that. And what we want is a thing is probably gonna be. Let's copy the name of the two columns. So we want D by category, right? So we want the cell ID against, so that will be the rows, one column, and this will be the second column, and the function that is going to integrate cell ID by number is going to be called length, which is count. So let's see what this does. So we type ANS. Okay, this is probably not the one that I wanted to do. So I'm just gonna All right, so here I found this web page that does the job for us. I mean, again, trying to find out how to count the number of heat anomalies at each grid cell, and I just typed there how to group data on a data table, and I found this one here. And again, if you look at the structure of this line of code, it has DT, which is the name of a database that they created, comma, so just all of the rows, then this thing, and then it lists the variables. He wants to group two things, and he wants to group that by date. All right, so let's see if we can adapt this to our database. Sorry, I just have some information there that is not important for now. All right, so this is the line of code that somebody else using the internet, again, to group information from a data table. So here you can copy the name of the data table or the database list. This is the name of the variable, so we're gonna call it number heat anomalies, and that's gonna be equal to the sum. Let's use some, for instance, just some values there. Let's sum we had our database. So we are gonna sum the number of heat anomalies just to see what it does. So again, if we come back to our original line of code, we had again the name of the database. We are creating a variable that is called number of heat anomalies, and we are gonna sum the string events. We can delete this, which is another thing that they wanted to calculate there. We delete that comma, and we want to group that by cell ID, which is obviously what we want to do. We want to count all of the heat anomalies on each cell ID. So now we can run this line of code and see what it does. So there you have it. You have cell ID, and this is the summatory of all of the number of events. Obviously, the problem that we had here is that we need to replace this function sum for something else. We can potentially just count, for instance, the number of rows that are occupied on this database by each one of these LIDs, and that will tell you how many rows are there. So in Excel, sorry, in data table, the way to count the number of rows is by using the dot and n. Right? That will tell you just how many rows are occupied by each cell. We can copy this. So here again we just counted the number of heat anomalies. Again, for the cell ID number 1, if you remember, there were 16 heat waves that happened in 1950. In this cell ID there are only eight heat anomalies. So now that we know that that works, we can do exactly the same thing. Sorry, we need to put this as a variable, as a name. So we are going to call heat. We're going to call it the same thing, but we're going to call it 2. Right, so we created a second database of the heat anomalies in 1950 that now is grouping all of the heat anomalies by cell ID, just to count how many heat anomalies are in total in 1950. And we can see, we can do it now for the year 2099. We need to replace the name of the database here, 2099, and we want to do the same grouping again. Just generate a variable that is called heat anomalies 1999. All right, so we can run this. You can see what the variable is now. You can see, for instance, on the year 2099, this cell ID actually has just 12 anomalies. It's interesting actually that there are less heat anomalies in the future than what they are in 1950. Now what we want to do is to merge these two databases just to see how similar or different these places are. So for you to do that, you need to first, you remember, you need to set a key for every one of those databases. Set key for this database 1950. The key is going to be cell ID. Again, we want to group everything by cell ID, and we also need to set a key by to the second database from the 2099. Right, so we can just copy these two keys and we can paste them in our sorry, that's because we didn't run this line of code after we entered the name of the right there. So again, we had two databases, 1950, 2099, that had a similar cell ID. So now, because the two databases had a similar key, the cell ID, now we can use the function merge, right? So we're going to call it heat waves. And that's going to be equal to merge. We're going to merge by 1950, and we're going to merge it with the database from the year 2099, and we can close brackets, and now we can run that code in R. Right, so now we had a database that is combining the two data tables for 1950 and the year 2099. Obviously, as you can see, Excel, because they had the same name, the two variables are named the same, R tried to put a unique name to those two columns there. So one thing that we can avoid here is right on this line of code, after we created the database. Sorry, actually we can do that here, is we can change the names of those columns so that they are different for the different years. So we call say names. We enter the name of the database. So now you look at that database for 1950. The column that we want to change is this one, and we want it to be specific to the year 1950, right? So we go back to over here. So we enter the name that it has right now, and then we enter the name that we want to put there. Heat anomalies 1950. So that will change the name of this column in that database. I think that you have to put this between quotations because it's test. And now we can run this. this line of code. So now if we look at the database again, now you can see that we just changed the name of that column there, so that now when we merge them, we know the year of every one of those two columns. So we can do exactly the same thing now for the database for the year 1999. And we want to change the name of the column that is called num heat, and we want it to be now 2099, right? If we run that line of code, you will see then that that changed from this database of the number of heat anomalies in 1999. It changed the name of the column to the year 2099. Now what we want to do is now we can merge the two of them. And now if we look at what the database, how that database looks, so that you have it. So you had here the SLID, again this is a place in the planet. This is the number of heat anomalies in 1950, and this is the number of heat anomalies in the year 2099. Let's do a quick plot of this just to see how those two, how the heat anomalies compare between 1950 and the year 2099. So we type heat waves. You remember to select the column, you put the $, then you put the name, the first column, this sign, and we want to plot that against heat waves, but against this using this column instead. Then we plot it there. All right. So what we had here, again, this is all. So you can see the places that today. So this is in the year 2099, and this is in the year 1950. I mean, you can see that, I mean, there seems to be no variability whatsoever in how many heat anomalies are on every place. Now, one thing that we can do here is, for instance, we can calculate the mean of heat anomalies in 1950. So on average, globally, in the year 1950, there were 15 heat anomalies, and we can do the same thing for the year 2099. And you can see, actually, there are some differences there. There were, by the year 2099, on average, every place in the planet will have about 23 heat anomalies, but in the year 2015, there will be only about 15. Obviously, you can tell that they're, on average, they seem to be bigger, but here when you plot the heat anomalies, it seems that every pixel had it's not really a clear trend there, right? So now, how do we analyze this statistically, though, just to see if there are significant differences between 1950 and the year 2099? So one way to do it is to use something that is called a t-test. So you can just go to Google and type how to do a t-test in R. T-test is just a way to compare significant differences between two means, right? Just to see the mean value, the average value of those 2 years are different from each other. So that's usually the statistic that you use. So this is how you run it in Excel. Let's just look quickly at an example here. So let's look at how this is done in R. So we copy the name of the function. That's how you do a t-test in R. Put the quotation mark, type the function, and let's see what how that's supposed to do there. So again here, t-test, if you remember, is just to compare where two means are different from each other, and it's asking you to enter the x and the y value. I suppose this is the variable number 1 and the variable 2. What I want to see here, all right, so you see, again, as I told you, t-test is just a way to compare two means. So here is comparing, for instance, the significant difference. If you look at this one here, it's comparing the significant differences between these x, which are the numbers 1 to 10, and a variable y, which is from 7 to 20, right? So let's see, let's run that line of code in R. Sorry, before we actually interpret the results of the t-test, let's just look at the two databases that they try to compare. So they try to compare this x to this y, right? So let's copy this line, 1 to 10, paste it. So basically, again, the first group of numbers is, again, the numbers 1 to 10, and the second group of numbers is this part here, which is y equals 6 to 29. So you type y. So this is the second group of numbers, right? So the t-test, just comparing whether there are significant differences between this first group of numbers, x, and this second group of numbers, y. Now, again, we can, after you run that, you can see here the results. Remember what I told you about the p-value, which is the thing that we really need to interpret. The p-value, again, is where those two groups are significantly different from each other. You got a p-value smaller than 0.05, again, 0.05. That means that the groups are significantly different from each other. So here we had a number that is 0.0001. So this number is super small, suggesting that there are indeed significant differences between these two groups. And obviously that makes sense. If you look at these numbers here, this is the first group, which is from 1 to 10, and the second group, most of the numbers are larger than 10. So this t-test tells you that indeed they are significantly different from each other. Another interesting thing of the t-test is that it gives you the mean value. So on the first group, the average mean value for x was 5.5. For the group y, the average value was 13. And obviously those things were significantly different from each other. So let's try to do the same thing now, but for our database though. So let's copy this line of code. So what will be the first group of things that we want to compare? So what we want to compare, again, if we look at our database heat waves, we had two columns there. So we had this column and that column. So we want to compare this group. That will be here our x. And we want to compare against this, the heat anomalies from 2099. And that will become our y, right? Keep in mind that here we have only told R about the name of the variables. So, but they don't know, R in this moment doesn't know where are those variables. So you need to, you remember, you need to first indicate the database where that variable is located. So that's usually put at the front, the name of the database, separated with the $sign, and you do the same thing for the year 2099, and you enter the $sign. Then we can run this line of code. And here you can see it. Again, there seems to be significant differences. Again, look at the p-value. The heat anomalies in the year 2099, which is our variable y, was 23, while the mean number of heat anomalies was 15 for the year 1950, and this is how significantly different they are from each other. Now you go back to the tutorial on how to use the function t-test in R. Another interesting thing here is that it allows you to also do a plot. Okay, I think that you can guys figure that out by yourselves now, how to make a plot on this. But anyway, there you have it. That's how to run a t-test in R. And from this database, again, you can tell that there are indeed significant differences in the number of heat anomalies between the year 1950 and the year 2099. That's of course assuming that the planet is going to continue heating up as it has so far. One thing that I want you to do now is you go back to the original database, try to repeat the same tutorial that you just did, but instead of counting how many heat anomalies, you remember this is the original database, 1950, you had the number of heat anomalies, but another thing that you had here is this variable called duration, right? So what I want you to do is repeat this entire tutorial, but now calculate the average value of how long those heat anomalies were, right? So the homework for you for Monday or Wednesday is gonna be to give me a sense on what is the average duration of the heat anomalies in every one of those 2 years, and where there are significant differences between 1950 and the year 2099. All right, guys, I see you Monday.